Hello and welcome to our section 2.3 lecture video for today. So to start out today, we're going to talk about families of functions and transformations. So what I'd like you to do, notice I've already graphed these graphs here on page 19 as well as the ones on page 20. But what I'd like you to do is pause the video for a moment and use class calc to draw these same graphs. Then once you start back with the graphs, we can talk about them. So if you look, so go ahead and take a moment and do that. Okay, so now that you've got all these functions graphed, what we can do is talk about what happened. So notice here, all we've done to change these three graphs is either added or subtracted 3 from the outside. So what effect does adding a number to the square root of x have to the graph? Well, what it does, as you can see, is it moves it up. Okay, so it moves the graph up by that number. Similarly, what happens if I subtract a number from the square root of x? Well, as you can see from the original here, it moves it down by that number of units, to be more specific. Okay, so adding or subtracting a number outside of the function simply moves the graph up or down. Now notice here, instead of subtracting the number from the square root of x or from x squared, I subtracted it before I took the squared. And notice if I subtract it before I take a square, it moves it to the right by that number of units. And if I add before I do the operation, it moves it to the left by that number of units. So if we add or subtract after we do the operation, it moves it up or down. If we add or subtract before we do the operation, in this case squared, it moves it left or right. Then if we multiply by things, it has other effects on the graph. So first of all, what you should notice here is if I multiply by a negative, what's happening to the graph? Well, it's being reflected across the x-axis. So by taking the opposite of function, we reflect it across the x-axis. So the exact same graph, but now just pointing down. And then if we multiply by a number out in front that's positive, we have a different effect. What it does is it changes the y values by that value. So it either stretches it or shrinks it by that value. So if we multiply by 2, then that's going to stretch the graph vertically. And if we multiply by a fraction that's less than 1, we're actually dividing by a number, so that's actually going to shrink the graph vertically by that factor. Okay, so those are the different transformations we're going to do, and so there's quite a few examples of these. So what we can do is we can take all that information and we can put it together in one place using this idea of what we're going to call family of functions and transformations. So if a, h, and k are real numbers, then the graph of y equals a times f of x minus h plus k is a transformation of the graph of y equals f of x. If we take all the transformations like this using the same f of x, we call them a family of functions. So some examples of families of functions we're going to look at are things like y equals the square root of x. So all the ones that fall into that family would be things that look like this. Y equals a times the square root of x minus h plus k. Or we'll look at y equals x squared. So all the ones that its family will all look like this. A times x minus h squared plus k. Or maybe we'll look at the absolute value of x. So all of its look like this. Y equals a times the absolute value of x minus h plus k. So the idea is any function that only involves one operation besides addition, multiplication, subtraction, or division can fall into a family of functions based on the last operations that's left here. So we're looking at ones that are the square root squared and the absolute value. And then these transformations that we're going to look at fall into two different types of transformations. So if a transformation changes the shape of the graph, then it is non-rigid. And if it doesn't change the shape of the graph, it is a rigid transformation. So the first set of our transformation is the idea of translation. So to translate a graph just means to move it either vertically or horizontally without changing the shape. So we're just moving this around the graph. So as we saw on the last page, if we have a positive k, if we add, so this is adding k, we saw on the previous pages that this means that we move the graph k units upward. And if we subtracted k, if we made k negative, so we subtract k, that was going to move it down. Now, if we plug a positive number inside the function like this, f of like here, notice that that would mean that would leave that as a subtraction. So in this case, if we subtract h, then we're going to move it to the right. Notice that might seem a little bit backwards because our negative numbers are to the left and our positive numbers are to the right. But it's because of this negative in the formula that makes that move to the right. So h is actually positive even when we're subtracting it. And if h is negative, then we're going to end up adding it. So if we add h, that would move it to the left. So if we add inside the function, that's going to move it to the left. A reflection is the mirror image of the graph across the y-axis. So that means the graph of y equals the opposite of f of x is a reflection in the x-axis of the graph of y equals f of x. And last but not least, if we multiply by a number a out in front, that is either going to stretch or shrink the graph vertically. Okay, so it's like grabbing it on the top and the bottom and pulling apart, or pushing together, depending on if it's a stretch or a shrink. So one of the things we ought to be able to do is we ought to be able to take this idea and take a basic function and translate it using this idea. So like, for example, if I have the equation y equals x squared, and I want to translate it 13, I start with that. So I start with my basic function, and then I do each one of the operations. So I want to translate it 13 units to the right. So as we saw on the previous page, to translate it 13 units to the right, I subtract 13 from x before I square it. And then it says I want to use, so that moved it 13 units to the right. Then I want to move 6 units down. So to do that, we subtract 6 after we do the square. And then we wanted to reflect this in the x-axis. So that means we need to take the opposite of the whole thing to reflect it. And we can simplify that by distributing the negative and getting the opposite of x minus 13 squared plus 6. Notice, because of the order we did those things in, it changed this last sign. So if we use our Class Calc app briefly here, we can see these transformations in action. So if we start with our basic function, y equals x squared. Oops, sorry, missed the equals. Equals x squared. There's our basic function that we start with. So let me zoom out a little. Okay, and so now if I put the minus 13 in the middle here, well, let's go ahead and just write that as a different function. So if we add the minus 13, so x minus 13 squared, notice how that moved. Whoops, I missed the 13. The 13, that moved it 13 units to the right. Okay, and then if we add in the same function, so y equals x minus 13 squared. And now we want to move it 6 units down, so we subtract 6 from that. See how that moved it 6 units down? And now, if you see that I want to reflect that across the x-axis, what I want to do is flip it over. So I want a reflection of that. So what I want to do is do y equals the opposite of the whole thing, like we did on our paper. Because we're reflecting across the x-axis. And notice how that the blue one over here on the right-hand side is a reflection across the x-axis of this brown one. However, if I hadn't done that, if I just put the negative out in front, and I didn't distribute the negative, so this would still be minus 6. Notice how that red one is reflected not across the x-axis, but across this vertex, this point here where the two graphs meet. And that's not what we want. It said it was reflected across the x-axis. So that's why you need to, whenever you do the negative, you have to take the opposite of everything you've already done. Okay, so there's one example. So another example, the second one here says we start with the graph y equals x, so a linear equation. And then we're going to stretch it by a factor of 2. So if we recall, stretching it by a factor of 2 means I'm going to multiply it by 2. And then we want to reflect it, so I'm going to take the opposite of everything I've done so far, so negative 2x. Then I'm going to translate it 8 units downward, so y equals negative 2x minus 8. And then it want to go 6 units to the left. So the thing you want to remember about going left and right is you want to do it before you do anything else. So to go to the left, we add 6 to x before we do anything else. So it'd be negative 2 times x plus 6 minus 8. So inside the parentheses. And now because this is a linear equation, I can simplify it a little bit. I couldn't do that here. I mean, I could have simplified this if I wanted to write it differently, but I would have had to multiply out this squared on the first problem, which is more hassle than it's worth. But here I can just go and distribute. So this would be y equals negative 2x minus 12 minus 8. So that would be y equals negative 2x minus 20. Okay, so just like we did last on the other video lectures, at this point, go ahead and pause the video and try the other two. And then when you start the video back up, we'll go through the answers. Okay, so let's go ahead and go through these two answers. So in this case, all we're doing is translating 7 units to the left. So if we remember, translating 7 units to the left means adding 7 inside the parentheses before we do the square. And then with this last one, we want to go 5 units to the left and then 12 units down. So to go 5 units to the left, we add 5 units before we do the square root. So x plus 5 goes under the square root. And then to go down, we do that after the square root. So that would go outside of the square root. So it would be y equals the square root of x plus 5 minus 12. Okay, so that's how you could write the equation given the transformations. So if you knew what the basic function was and you knew what the transformations were, you could write the equation using that. What we'd also like to be able to do is we'd also like to see what do these transformations do to the ordered pairs of an equation? How does it change what an equation is? So what we want to do is we want to just practice this idea of changing ordered pairs. Okay, so if we do that, what we want to know is from a formula that looks like this, what happens is if I have an ordered pair of the formula, so let's just call it x comma y. So we know the h moves the graph left or right. So to change the h is going to affect the x. So we can do that the x coordinate is going to become x plus h. And we know the y coordinate is affected by k. So that's going to be y plus k. And we also know that a affects the y values as well. So we're going to multiply a times y. So if you have an ordered pair x comma y of the original function, then the new function ordered pairs will be of this form: x plus h comma ay plus k. So let's go ahead and try one of these problems. So the first thing they want us to do is name the basic function it is a transformation of. So in this case, the basic function, if I get rid of all the transformations, is y equals x squared. Okay? So that's step one. So then step two is we want to get some ordered pairs for that function. So one ordered pair I could do would be, you could pick any 3 points. So I could do 0, 0, right? If I plug in 0 into the basic function, I get 0 out. I could do 1 comma 1, right? If I plug 1 into this basic function, I get 1 out. And we could do negative 2 comma 4. If I plug in negative 2 into the basic function, I get 4 out. So now I can take those 3 basic functions and use this information up here at the top of the page to find the 3 new points. So from our equation here, we can see, so this is for part 3, that a is 1, right? Because there is no number being multiplied out in front. H is negative 5, because this should be the opposite of this number, right? Because it's minus h. So for this to be a plus 5, it has to be a negative 5. And then k is negative 4, right? Because we've got to subtract 4 out there. So what we can do now is use this information up here at the top to find these new points. So 0, 0 is going to be 0 minus 5, comma 1 times 0 minus 4. And the next one's going to be 1 minus 5, comma 1 times 1 minus 4. And the last one's going to be negative 2 minus 5, comma 1 times negative 2 minus, that one is not correct. Not negative 2, the y coordinate over here, which is 4. So 1 times 4 minus 4. So our new points are negative 5, negative 4, negative 4, negative 3, and negative 7, 0. So that's the first part. So those are finding the points. Now the domain works in kind of the same way. So the range. So the domain of a function, what we're going to want to do is you're going to want to take, so to find the domain and the range, so for the domain, what you want to do is you want to take any endpoints and add h. And for the range, take any endpoints multiply by a and then add k. So in this case, in the original function, the domain of the original function is negative infinity to infinity. So I don't have any endpoints, right? Because negative infinity to infinity. So the domain of the translated function is just going to be negative infinity to infinity. For the range of the original function, y equals x squared, which we've talked about yesterday, its range is, or in our last video, is 0 to infinity. So we multiply this by a, which is 1, so that's still 0, and then I add k, which was negative 4. So the new range is negative 4 to infinity. Okay, so that's how the numbers in the equation affect the ordered pairs and the domain and range. Okay, so we could go ahead and try another one here, doing the same idea. Okay, so we start out by finding the original function, So in this case, the basic function is y equals the square root of x. So that's part 1. Then part 2 is to find some ordered pairs for that function. So some ordered pairs of the square root of x would be 0, 0 is one good example. We could do 1, 1, and we could do 4, 2. Okay, so those are all ordered pairs of the original function. So then for part 3, we can tell what our a is, which is -1/2. Our h is, which is -2, and our k is +4. And then we just use the information at the top of the page to plug in this information. So our new ordered pairs, it's our old x plus h, so in this case -2. And then it's our old y times a plus k, so +4. And then it would be 1 minus 2, comma -1/2 times 0, times 1 times 1 plus 4, and then our last ordered pair, 4 minus 2, -1/2 times 2 plus 4. So that means our new ordered pairs are -2, 4, -1, -1/2 times 1 is -1/2 plus 4 is 7/2, 3.5, and then the last one would be 2, comma, -1 plus 4 is 3. So there's our new ordered pairs. And then the same thing happens for the domain and range that happened above. We list the original domain, which in this case is 0 to infinity, and the original range for the basic function, which is also 0 to infinity, right? If you're not sure about those, you can graph it and look at the graph and see what the domain and range are. And then for the domain, we add k to this, so k is h to this, so h is -2, so the new domain is -2 to infinity. And for the range, we multiply by a, which is 0 times -1/2 is still 0, and then we add k. So add k. Sorry, one thing I forgot to mention at the top is if you multiply by a negative, you have to flip the interval. So this would be -infinity to 4. So let's go ahead and add that back to the notes at the top. So is if a is negative, reverse interval. So notice that's what we did down here. We had to flip that interval because we multiplied by a -a. Okay, so why don't you all take a few minutes and try doing the same thing for these problems on page 24. So go and pause the video, try these, and then when you're done with those, you can start the video again and we'll go through the answers. Okay, so for this first one, the first thing we do right is we name the basic function, so that's the absolute value of x. So then we can get some ordered pairs for that. There's a lot to choose from, but I'm going to use 0, 0, 1, 1, and -2, 2. But you could have obviously used different ones, so if you got different answers because you use different ordered pairs, that's perfectly fine, as long as those ordered pairs are correct. In this case, a is 3 and h is 2. So our new ordered pairs would be 0 plus 2, comma 3 times 0. 1 plus 2 times 3 times 1. And then last but not least, -2 plus 2 and 3 times 2. So our new ordered pairs would be 2, 0, 3, 3, and 0, 6. Okay, and then we do the same thing we did before for the domain and range. So the domain is -infinity to infinity. So that's going to stay the same because if you add 2 to those, nothing happens. And then the range here is 0 to infinity. And so we multiply that by 3, and so that's not going to change this either. So our range is still going to be 0 to infinity. Okay, so that's the idea. So let's keep going through the other ones. So the next one, 1, the basic function is the square root of x. Some ordered pairs for the square root of x are, we could use the same ones we used before. So 0, 0, 1, 1, 4, 2. Then to do part 3, a is 1, h is 3, and k is 2. So our ordered pairs, we add h to our x-coordinate, and we multiply a times our y-coordinate plus k. So it'd be 0 plus 3, comma 1 times 0 plus 2, 1 plus 3, comma 1 times 1 plus 2, and 4 plus 3, comma 1 times 2 plus 2. And so that gives us 3, comma 2, 4, comma 3, and 7, comma 4. And so now for the domain, we start with 0 to infinity, and we add 3 to the endpoint, so that becomes 3 to infinity. And for the range, we started with 0 to infinity, and we add 2 to the endpoint, so that gives me 2 to infinity. And then the last one here is the same idea. Okay, so we start by writing the basic function, which is y equals x squared. So number 1 is y equals x squared. So we could use the same order pairs that we used when we did the x squared one on the previous page. So 0, 0, 1, 1, negative 2, 4. In this case, our a is negative 1, our h is 1, and our k is 2. So we are x1, so this will be 0 plus 1, comma negative 1 times 0 plus 2. 1 plus 1, comma negative 1 times 1 plus 2, and negative 2 plus 1, comma negative 1 times negative 2 plus 2. Sorry, except I did that one wrong. This should be a 4. The y-coordinate gets plugged in here. So that's 1, comma 2, 2, comma 1, and negative 1, comma negative 2. And just like on the previous two, when we go to do the domain and range, we start out with the original domain, which is negative infinity to infinity, and the original range for the basic function, which is 0 to infinity. Nothing affects the domain, so it's still negative infinity to infinity because it doesn't have any endpoints. But for the range, we have a negative a, so we need to flip it. So it's going to be negative infinity to something, and then we need to add k to the endpoint. So 0 plus 2 is 2. So there's our new range. Okay, so that's the idea of how transformations work and how the equations for these functions are related to one another and related to their graphs. So now that we've talked about that, we can talk about a couple more things that are in this section. The first of which is symmetry. So one of the things that's true about functions is they can be considered either even or odd or neither. So if f of the opposite of x equals f of x for every value of x in the domain of the function f, then f is called an even function, and it's going to be symmetric about its y-axis. And if f of the opposite of x equals the opposite of f of x for every value of x in the domain of f, then f is called an odd function, and its graph is symmetric about the origin. Okay, so to figure out if something's even or odd, what we need to do is we need to find f of the opposite of x and the opposite of f of x. Okay, so to find f of the opposite of x, you just plug in the opposite of x for x in the function. And to find the opposite of f of x, you just take the opposite of the whole function. Okay, and then we want to compare these three. So if I multiply out the first one, I get x squared minus 2x plus 1. If I multiply out the second one, I get x squared plus 2x plus 1. And if I multiply out the last one and distribute the negative, I get the opposite of x squared plus 2x minus 1. So the question are any of those equal to each other? So does f of the opposite of x equal f of x? Or does f of the opposite of x equal the opposite of f of x? And if we look at those, none of those are the same, so the answer is neither of those. So this has neither symmetry. Okay, and so that's just the idea. So then we can try the next one. So the next one, we want to do exactly the same thing. So f of the opposite of x and the opposite of f of x. So in this case, this would be the square root of 9 minus the opposite of x squared. And this one would be the opposite of 9 minus x squared. And then we can simplify if possible. So in the inside here, how many negatives do we have? Well, we have 1, 2, 3, right? Because this is squared. So that negative is there twice. So we have 3 of those, which means this is the same as writing 9 minus x squared, right? Because if we multiply 3 negatives together, we get a negative. So what you should notice is f of the opposite of x is equal to the original. So that means that this is an even function, and it has y-axis symmetry. Okay, so there's an example of an even function. And then notice that this one is not equal to either of these because it's the opposite of those. So those are not equal. Okay, so we could try a third one here. So down here, we just do the exact same thing, right? F of the opposite of x and the opposite of f of x. So f of the opposite of x here would be the opposite of x cubed minus the opposite of x. And down here, we'd have the opposite of x cubed minus x. And so there are 3 negatives here because it's cubed. So that would be negative x cubed. And here there are 2 negatives. So that's going to be positive. And then here I can distribute the negative. So this would be the opposite of x cubed minus x. Plus x. Sorry. So what you should notice is these two, f of the opposite of x and the opposite of f of x, are the same. Which means this is an odd function and it has origin symmetry. Okay, so that's the idea. So why don't you all take a few minutes and see what you get for the pause the video and try these other 3. Okay, so now that you've tried these other 3, let's go and talk about them. So we're going to do exactly the same thing we did for the first ones. So we'll do f of the opposite of x and the opposite of f of x. So for this one, it's the opposite of x to the 6th minus the opposite of x to the 4th plus the opposite of x squared. And this one, we're going to have the opposite of x to the 6th minus x to the 4th plus x squared. So for this first one, if I have 6 negatives, right, because it's the 6th power, that's even, so that means that's positive. Here I have 5 negatives because I've got the 4 from the negative x to the 4th plus this one, so that's odd, so that's negative x to the 5th. And here I have negative x squared, so that's 2. So that's even, so that's a positive term. And then if I distribute the last one, I get the opposite of x to the 6th plus x to the 4th minus x squared. So if we look at all 3 of these, what you should notice is the original is equal to the opposite of f of x. So the f of the opposite of x is equal to the original. So what that tells us is that, similar to the second problem, this is an even function with y-axis symmetry. Okay. So there's that one. So then the third one here, f of the opposite of x and the opposite of f of x. So that would be the opposite of x minus 3 and the opposite of x minus 3 like that. So that would be the opposite of x minus 3 and the opposite of x plus 3. And if we look, none of those are equal to each other. So this one has neither. And then for the last one, if we do f of the opposite of x and the opposite of f of x, this would be the opposite of the opposite of x, and this would be the opposite of the opposite of x, which are both x. So f of the opposite of x equals the opposite of f of x, which means that this is an odd function, and that it has origin symmetry. So now one thing before we move on is we want to look back at all of these and see if we can see any patterns. And if you look, what you should notice is the ones that are odd, all of the exponents are odd. So this one we had a 3 and a 1. Here we just have a 1. So all of the exponents were odd, so that was an odd function. For the two that were even, what you should notice is all the exponents are even, or we have a constant term. So here we've got the 6th, the 4th, and the 2nd. Here we've got the 2nd and a constant term, which is 9, and those are both even. And then for the ones that are not even, what you should notice is you have a mix of odd terms, even terms, and or constants. So like up here, I've got an even term, an even exponent, an odd exponent, and a constant term. And then down here on this one, I've got an odd term and a constant. And so those were neither. So a really quick way to tell if something is even is ask, are all the exponents even, or is there a constant term? And or is there a constant term? And then for odd, you just want to ask, are all the exponents odd? Okay, so that's where they get their names. Okay, and then the last thing in this section is simply using graphing to help us solve more complicated inequalities. So the idea here is what we're going to do is we're going to graph y equals 2 minus the absolute value of x plus 1. So what we're looking for is y to be greater than or equal to 0, right? That matches up with that. So what we're asking is for what x value, what ordered pairs are the y's greater than or equal to 0? Because I want this thing to be greater than or equal to 0. So if I graph that, so let me go ahead and get rid of all my other graphs. So y equals 2 minus the absolute value of x minus 3, I think. Let me check that to make sure that's what I want. And it went all the way back to the beginning for some reason. Okay. So if we look at, plus 1. Okay, so not plus, minus 3 plus 1. Okay. And if I zoom back in here a little bit, what you should notice is here's all the the x-axis is where the y values are 0, right? If I graph those, I've got my x values that are negative 3, 0, and 1, 0. And I want to know, where is this thing greater than or equal to 0? Well, where are y values greater than or equal to 0? When they're above the x-axis, right? These y values, 0, 1 is positive, and this one's positive. So the part of the graph that is greater than or equal to 0, that's greater than 0, is this part above the x-axis. And then the parts that are equal to 0 are actually when we hit this, and everything below is negative. So if I transfer this into our notes a little bit, I can draw a little sketch of this. So here's my axes. And now we can draw our graph that look like this. And we had this point as negative 3, 0, and this point was 1, 0. And on the graph, what we're looking at is anything above the x-axis is where y is greater than 0. On the x-axis is y equals to 0. And below the x-axis is y is less than 0. So in this case, what we're looking for is we're looking for these two. We can be equal to 0 or we can be greater than 0. We want y to be those. So the place where y is those is this part that's above the x-axis. So that would be all these x values. And the answers are the x values. So I take this endpoint on the end, that's -3 to 1, and I get all the points between those. And then in this case, because it's or equal to, I want to include them, right? Just like when we were doing inequalities in chapter 1, when we have or equal to, we include the endpoints. And so that's all there really is to these. So let's try another one. So we start out by setting y equals to x minus 2 squared. And actually, sorry, there's one step I forgot for this first one before we do that. One of the things you want to do is the easiest way to do these is always compare them to the x-axis. So we want to set one side equal to 0. So I actually start this problem by subtracting 3 from both sides. So these cancel, and I get x minus 2 squared minus 3 is less than 0. So I want y to equal x squared minus 2, x minus 2 squared minus 3. And so we're looking for y to be less than 0. So in this case, we're going to be looking for y to be below the x-axis. So if we graph that, okay, so replace this graph with the one we just did. So y equals x minus 2 squared minus 3. Okay, and if we look at this one, we can see, oh, okay. Yeah, so if we look at this one, we can see that we're looking for, this is our graph, and here's where it's equal to 0. But notice that these are decimals, and not necessarily decimals that we know how to deal with easily. So we're probably going to have to do a little bit more work to deal with this problem than with ones we've done previously. And we'll get to that in a second. But we can still see which part of this is the answer. It's the part that's below the x-axis. So that means our answer is going to be between these two endpoints. I don't know what they are yet, but I can tell you right now that I want below the x-axis. We're not or equal to, so I'm going to use parentheses. So this is going to be something, comma, something, and that's going to be my solution. I just need to figure out what those endpoints are. And so what I want to know is, when is this thing equal to 0? So we can solve, and I'm going to do it over here, I think. X minus 2 squared minus 3 equals 0. And we can solve that. And you can multiply that out and use the quadratic formula, or I'm going to use the square root property. Right, so this would be add 3 to both sides. So this is x minus 2 squared equals 3. Then we can use the square root property. So this is x minus 2 equals plus or minus the square root of 3. And then we can add 2 to both sides to get x equals 2 plus or minus the square root of 3. And so those are our two endpoints. We've got 2 minus the square root of 3 and 2 plus the square root of 3. So what this allowed us to do to solve this inequality is we use the graph to figure out what the answer was going to look like, and then we can use algebra to find out when it is equal to 0, which is these endpoints. And if we add a little sketch to our graph, like we had for the last one, right, I could go ahead and add a little graph here maybe. So our graph looked like this. And so our endpoints are right there, and we wanted y to be less than 0. So that's this part down here. So that's the part under the graph, that between these two, right? If I had done y is greater than or equal to 0 here, it would have actually been these two parts above the x-axis. Okay. So let's go ahead and try a couple more together, and then I'll give you all a chance to try these. So let's go ahead and graph the next one. So we're going to graph 5 minus the square root of x. So y equals okay, and that looks like this. So let's zoom out a little and okay, so that's what this graph looks like. So in this case, we're looking for it to be greater than 0. So that's the part that's above the x-axis. So where does it hit the x-axis? Well, it hits the x-axis at 25. We want it to be above the x-axis, so that's all of this part of the graph that's above the x-axis. So if I drew a little graph of this in our notes, what this one would look like. Right, it would look something like this. So this point was 0, 5, and this part was 25, 0. And we want y to be greater than 0, right? We're doing greater than 0, so that's above the x-axis. So this one's a little tricky because I want this whole interval of the graph. So we've got from 0 to 25. 25 is not included because it was strictly greater than, not greater than or equal to. But is 0 a solution? Is when I plug in 0, do I get an answer that's greater than 0? Yes, I do. So I'm going to include that because that is an endpoint. So I'm going to include that one. So that one was a slightly odd one. And then let's try this one more together here. So the absolute value of x minus 2 minus 3. Okay, so y equals the absolute value of x minus 2 minus 3. Okay, so that looks like that. And so in this case, we can see we want the part that's above the x-axis, right? Because we want to be greater than 0. So above the x-axis is actually going to be two different parts here. So this is going to be like our OR compound inequalities, right? We're going to have these two pieces, which we're solving an absolute value inequality. That's not necessarily surprising, but this can help us do that. So if I look at these endpoints, these x-intercepts, I get -1, 0, and 5, 0. So in our notes, we could draw a little graph if we want. Okay, so this one looks like this. So we've got -1, 0, and 5, 0. And in this case, we're trying to be greater than 0, so we want the part that is above the x-axis. Well, that's actually two different pieces, right? That's this part over here and this part over here. So we get the region from -infinity to -1, union from 5 to infinity. So we get these two pieces on the outside. Okay, so at this point, go ahead and pause the video briefly and try these other two problems, and then when you start the video again, we'll go over the answers. Okay, so when you did these two, you should have started out, I hope, by graphing them. So if I go ahead and draw what these graphs look like. So this first graph should be I believe an x-intercept of -2, 0. So the graph should have looked something like this. And 4, 0. And so in this case, once again, we want to be greater than 0. So that's the parts that are above the x-axis. And I'm not going to include the endpoints because it's not or equal to. So this one would be -infinity to -2, union 4 to infinity. And then this other one, the graph should look something like this. So the end point over here should be at -3, -2. And the x-intercept should be at 1, 0. So the graph looks like this. And in this case, we want to be less than or equal to 0. So that's the part that's below the x-axis. So that's this part right here, right? So that goes from -3 to 1. And we include the -3 because it's an endpoint within the region we're looking for, and we include the 1 because it's or equal to. Okay, so I think that is it for this time. Yep. So hopefully you're keeping up with all of your notes. This is all the material for the first week of online only classes, so hopefully you're catching up with all this stuff. Look out for emails about virtual office hours.